Dr. and Frank. So it's really a pleasure to end our day with Frank, who is my former PhD student and postdoc, who's gone on to do great things. And in particular, Frank is what I hope is the first of many of my students to substantially exceed my H index. So it's always nice when your students go on to have huge impact in the world, and that's definitely right. So he's now a fancy professor in Germany, which is a country that has a sort of fancy professorship sort of system. But that wasn't enough for him, so he became a second kind of fancy professor at a different European university on leave from his first one. And I think even that's not enough for him, because now he's come upon a new kind of research topic that's so exciting that he has now sort of, I'm allowed to say, he's started a company based around commercializing this crazy idea, which I think he's going to tell us about, which I hinted at before when Frank was still exploring habits. But this idea that somehow classification can be replaced entirely through appeals to multi-foundation models. And before that, Frank was really instrumental in the AutoML community, which was thinks about how machine learning and optimization methods can be used to improve the performance of machine learning algorithms themselves. Before that, he's one of the foundational figures in the algorithm configuration community, and also has done much of other really significant work in the kind of space that these that we spoke about, sort of representation. So it's a great pleasure to have Frank here.
Thank you very much. You should take one. Okay. If anyone is interested in AutoML, there we have a famous speaker there, Kevin Leighton-Brown.
I'll give you 40 minutes and I'll show you.
All right. Yeah, so we have a conference in New York in September. There's a submission deadline for like a month after SML. So if you do some AutoML related stuff, consider submitting there. It's an awesome conference. Today I won't be talking much about AutoML, but I will be talking about this new, really exciting research area of foundation models for tabular learning. So we all know that foundation models have really revolutionized images or revolutionized text, but in tabular learning, yeah, we use gradient boosting from that's 20 years old, and we just this field really is ripe to be revolutionized, and we're trying to start to do that. Starting with stuff that I'll talk about. All right, so the preview is we learned the new algorithm for tabular data from TabPFN. It's a foundation model, it's like it clearly outperforms the previous best methods for tabular data sets, such as XGBoost, gradient boosting, etc. For small data sets with up to 10,000 data points and 500 features. Why small? Because it's sort of, you feed them the entire data set in the context just as you would to a GPT. This is on average, not on every single data set. There are some data sets where it's slightly worse, but the vast majority of data sets is much better. There's a breakthrough paper coming out about this next month. And yeah, but we're already really keen on trying it on all kinds of data. So I have a link to an API with the algorithm. All right, tabular data. What is the same? It's not as fancy. It's not. It didn't used to be as hot as images, text, and so on. But actually, this nerves every talk that had tabular data is just overflowing. I couldn't get into one talk where people were sitting on the floor and everything. It was like 300 people. So deep learning for tabular data is really kind of getting its ChatGPT mode right now. So what is this? It's sort of machine learning 101. You have features. You have a particular column here that you want to predict from these features. So every row is a data point, Excel tables, or you also have this type of data in relational databases. And the goal is to learn a mapping from the features to the response. In this case here, you have some omics blood values and want to predict does this patient have early stage Alzheimer's. You can wait 3 years, but then it's too late to actually treat it. So you actually want to predict it right now. That's sort of the standard machine learning. We're going to extract this into have an X train. Y train, X test, and this is what we want to predict. This has tons and tons of different applications. For example, credit scoring, where your features would be income, credit history, credit amount, and so on. The prediction is, will the credit be paid back? Medical data, where the features are symptoms, measurements, and we want to predict which disease. And you see just from these two examples, it's just different columns. They don't really have anything to do with each other. And that's why deep learning foundation models just haven't cracked this yet. So the way we're going to tackle with this with foundation models is very different. We're going to learn an algorithm with context learning that doesn't care what the features are. All right, tabular data is the most common type of data, at least in the enterprise. Yet deep learning didn't traditionally excel in it. I basically said that what type of algorithms have we been using? SVMs back then, random forest, gradient boosting. It's also the poster child of AutoML. So AutoGluon, for example, the AutoWecker that we built with Kevin back then in 2013 was sort of the first real AutoML system for tabular data. Then we built AutoSQLearn, and now Amazon has put an amazing amount of engineering and really great engineering into AutoGluon. These are the types of methods that have been used so far. Neural networks there's been a lot of claims of neural networks doing great on this, and these claims have sort of always been refuted because deep learners didn't really know what they're doing, and benchmarking and fair comparisons and hyperbound optimization of the baselines. And so it really didn't ever stick. Why is this? Well, neural networks, they're slow to train, so it actually really is not what data scientists want. They want fast algorithm for ideation, for actually coming up with better features and so on. Slow doesn't really work very well there. And typically I've used small data sets. And on these small data sets, neural networks tend to overfit a lot. And so that's actually bad because we have a lot of these small data sets. So we have this long tail of small data sets. There's only very few large data sets. And then there's many, many small data sets in areas like biology, medicine, climate research, and so on. And we actually care about these small data sets. So we should come up with an algorithm that works well on small data sets. All right, TabPFN, what is this thing? So it's a GPT-like algorithm for tabular classification. That's if you frame this as next word prediction, you have the features for the first data point, then the response for the first data point, all the way to the features of the last data point, response of the last data point, features of a test point, question mark. So you want to predict the response for that particular new data point. To be a bit more precise, we don't have a sequence, but we actually have a set of data. We don't care about the order of these data points. And to be more precise, we want to predict a probability distribution and not just a point estimate. All right, so the high-level intuition about how we're going to go there is that we basically feed this here into a trained neural network, the PFN, and that outputs a probability distribution. This is parameterized by vector theta. It's a transformer, and that is actually so that single forward pass directly approximates this probability distribution for the test examples. We optimize these thetas simply to minimize the cross entropy across the test examples for many different data sets. Which data sets? Well, there's not actually millions of data sets out there in contrast to GPT. That was trained just on all the words on the internet, like billions and billions of them. We don't have billions of data sets, so we actually created them synthetically. And so that's a big part of the method is how did we create the data set that we then trained our method on. So I'll talk about that a bit. And then once we have this, it's really very standard. It's a pretty standard transformer. We just drop the position encoding in order to to treat it as a set rather than a sequence. And then it's just SG. All right. So some background. We had a paper previously on PFNs, not TabPFN, but PFNs, prior fitted networks, which was called Transformers Can Do Bayesian Inference. And so basically that can approximate the Bayesian posterior predictive distribution for any prior that you can draw samples from. So here's the visualization of some priors. So if you do Gaussian processes, for example, these are samples of functions that with particular criteria, such as being smooth in this case here. And then here is a particular posterior for these priors when you have observed a couple of data points. So this is the same type of plots you see when you do Bayesian optimization and so on. And yeah, so you have a prior over a function parameterized by these latents t, and then the posterior over these latents can be computed like this here. But this is intractable to actually compute exactly what you would do for this is Monte Carlo or variation of inference. And then once you have this, you integrate over this posterior yet to have your basically your predictive distribution for y given the latents of x. And so if this is MCMC, then this here is just a sum over the samples. And if it's variation of inference, then this distribution is typically Gaussian, and then it's a Gaussian times a Gaussian, and right out it's a Gaussian. What we do instead of MCMC and variation of inference is to just bypass this step here entirely and just directly only predict this here. So we say at this point x, what is a predictive distribution? And we can do that in a forward pass. And we don't actually ever get a posterior over the latents. It would be nice if you could do that. That is possible future work, but that is a limitation of our method. We don't get a posterior over these latents. We just have an approximation of the posterior predictive distribution. All right. So let me visualize this. So we draw samples from our prior. So we draw functions. And then we draw for each of these functions, we draw some data points, call some of them the training data points, the blue ones here, and some test, the orange one. And we do that for each of the functions. We don't need to draw the same number of data points from each. They can be spaced differently, etc. And then we do this a lot, 10 million times, or actually later on 130 million times. And then we learn a neural network to take the blue point and the x value for the orange point and predict the y value for the orange point. And if it can do that for a lot of different data sets, for a lot of different samples, then it just has learned to do that for the next function where it only gets a blue point. Then here we ask what is the predictive distribution there, and we do a forward pass and it predicts the distribution. Yes?
I'm just not seeing how you get a distribution out of predicting one point.
You predict the y given x. So you feed in the x and you predict the y given x. This is the input, so the data set, and then the x that you want the predictive distribution on. And
I'm just not seeing where the distribution is represented in the training.
It's you sample from the prior, you sample, so you could they could be functions with these blue data points, but where the orange one is actually here.
Oh, so
but there.
these are all sampled from the same prior.
Yeah, it's one prior, and you draw different functions from this prior,
Yeah.
and then data from each of the functions. So by drawing many different times from that prior, you actually have variation in that. And if the blue point really constrain the orange point, then your predictive distribution should be really tight because that's going to minimize cross entropy. But if it's not predictive about that, then you should have higher uncertainty.
Okay. I just feel like this is random functions, and so what do the functions across these samples have to do with each other that lets you predict given a specific data set?
So maybe it helps to see what it does. So these samples were from a Gaussian process, and the approximation is a posterior Gaussian process. It's like if you get the optimization to the minimum, if you minimize cross entropy loss, it probably is exact for the posterior approximation of the GP. So like, if you have a prior that you actually want to build the posterior for, that's what it does. But you need to choose a prior. So if it is truly GP, then well, this can be like that. But it could also be based on neural network. You could draw an architecture and then draw the parameters of this architecture and then do Bayesian inference over neural networks. It sort of just is it's much more flexible than the standard GP. Does that answer the question? Yeah. Thank you. Yeah, so in a nutshell, so we have meta-learned to approximate Bayesian inference by really simple tools. We only need supervised learning, SGD, that just works by now. And we need to be able to draw from the prior. And we don't need the really slow MCMC. We don't need the complex mass of variational inference. It's darn easy now. So of course, this has limitations. For example, we don't get a posterior over the latent. But if all we care about is a predictive distribution for a given data point, then we can just do this with forward pass.
Presumably, sample complexity is worse here. Presumably, you have a worse sample complexity here.
Sample complexity.
So how many things you have to see? 10 million, 50 million?
Yeah, but it's the prior is like that is one of our assumptions. You can sample from the prior. So you can sample as often as one from the prior. Yeah, very true. I mean, we need to sample a lot from there. In SMC, you don't need to expect the prior millions. Good. So let's move this to tabular data again. Back from PFNs to TabPFN. That's a tabular prior fitted network. So there we have this X train, Y train, X test. Then we mask out the Y test. We feed this into the TabPFN. That outputs a predictive distribution. And notice that this can be multimodal. And then you just look at the cross entropy of that prediction under the true of the true value under that prediction. And that's what you minimize. And you do that over millions of these sampled data sets. And then, so this here is all in synthetic data that's sampled. And then you see the first real data set here. You feed this in TabPFN and give you a prediction, done. And so really, this approximates a Bayesian posterior for the prior over data sets that we define. And so the whole step going from PFN to TabPFN was, let's come up with a prior of what could tabular data actually look like. And so there we went to structural causal models to integrate principles of simplicity and causality. And so we said, well, let's assume that there are some causal relationships and sample and initialize a causal graph that has at least as many variables as I have X and Y, but potentially some more. And let's sample some connections in there. Then let's sample where in this graph is X and where is Y. So Y is not always the thing that is a child, but it could also be the parent of some of the X's. In this case here, this here is the Y, and it causes one of the X's, and here's another cause of this X. And in the beginning of the graph, we actually have these epsilons. These are noise variables that are going to be sampled in order to actually sample data from this function. So this here is the equivalent. There's also some weights in here. It's in neural network activations and so on. You can make this arbitrarily complex. But then this represents a function, and you can sample from this function by sampling the epsilons, these inputs, and then just doing a forward propagation through this function. So we sample, in order to draw here 3 data points from this function. We sample the noise variables, push them through. This computation is deterministic, and then just read out where is, well, this here is supposed to be Y, this here is supposed to be X1, this is supposed to be X2. There we have sampled one data point, another data point, another data point. If we want to do classification data set, in this case binary, then we also sample the threshold and have sampled from one data set 3 data points.
Do you also have a partial
We have missing values in the prior later on.
or just not seeing some of them?
Yeah, so there's latents in there. Actually here, there's some. So you can have latents. You typically sample simple functions more frequently. So data functions that don't have too many latents, but you can also sample a ton of latents, just very complex functions. But we want to have this prior that we have simple explanations for data in order to just not overfit it. That's what you meant.
Yeah. I mean, because then, for example, you're saying maybe goes on, there's a whole this confounders that don't even exist.
Yes, exactly. So that's why we need to have the standard variables. All right, and yeah, then you can inspect these data sets. On the left here, we have some synthetic data sets where we just plot 2 features at a time. On the right, we have some real data sets. This is just to show, to me, for the naked eye, this looks sort of similar. And that's sort of the eyeballing we actually did when defining the prior. Does this look reasonable? Does this sort of look like real data sets? Qualitatively, when you do this, then and you basically sample data sets like this, millions of them, and for each of them you treat some of them as training points and some of them as test points, and so you learn to do tabular classification in these data sets across millions of data sets. So then you can do it on a new one, and if you do it on a new one, then you get predictions like this on some toy data sets here for visualization from scikit-learn. So there's this half-moon data set. You get very smooth predictions here, in contrast to, for example, decision trees, where it's just very, very axis aligned and rugged. It's trying to get you very smooth predictions because that tends to minimize cross-entropy loss.
So maybe I'm interested. So what's the properties of distribution of the data sets that you sample?
The property.
How many features? Which
Okay, yeah, I didn't say that. That's very true. So we sampled up to, so in the first version, we sampled only up to 100 features and up to 1,000 data points. So we sampled
all the numeric, all features.
back then all numeric, now not anymore. So I'll get to that in a second. But so the first version, we had a paper at Hector 2023. That was a limited version. That was only up to 1,000 data points and 100 features, and only continuous, and no missing values, and no imbalance, and so on. Many limitations that by now we have resolved. So
ranges of the numerical variables, distributions of them.
Yeah. So we actually we do a standard scaling before during training and test time, so we didn't need to look too much into the different ranges.
Scaling, okay, still the scaling the different distributions. Not ranges, but the distribution of the.
Yes, yeah, we also have different distributions. We have just pretty much what you can think of, we put in there. So all kinds of distributions. In order to, like, because
it's not structured. I mean, you just whatever you saw them, you put in, and that's it. Right?
More or less. So there was some random hyperparameter optimization based on some validation data set, but it was extremely limited. And really, the broader you make the prior, the more cases you tackle. Like if there's something that's just very different than your prior, then this is going to have a problem because it hasn't seen anything like that. So the true Bayesian procedure over this prior will actually be crap, and then this will be crap. So if you can make the prior broad enough to cover real cases, that is helpful.
Is there a specific reason you highlighted the word causal?
Well, they structured causal models.
But there's no interventions happening anywhere here.
There's no interventions. That is true, but
It's just also, you could also call it a base net. That's not right.
I did base that I'm actually sure it is directional. Yeah, we could call it base net. We do want to.
But interventions might make sense if you want to handle missing data.
Yeah, we do missing. We do that, but we just punch holes for that. So we first sample and then punch holes. But yeah, I mean we do. It's yeah, I mean it is a basic procedure of all possible structural causal models, and base nets don't. I mean, you don't typically have these types of variables in base nets, but I guess you can put them there.
It's probably your directions are meaningful in a generating sense. And for nonlinear functions, that has specific signatures in the distribution. So theoretically, your networks are probably identifiable data. If you're as nonlinear as I'm imagining you are.
It's definitely nonlinear. Yeah. Very fun. Yeah, so it's non-identifiable. I expect that, but you can do
No, I think they are identifiable. We can talk about that.
all right. Let's talk about that later.
Nonlinear makes stuff more easily identifiable in causal models.
That's okay. All right. So this is a sort of visually, this gives you very smooth predictions that are more akin to like nearest neighbors predictions than to gradient boosting. And yeah, they're well calibrated. But they also have this. This is my AutoML slide, which crosses out AutoML. This is sort of sad, but I have AutoML coming back later. Plus, so we did. It's like auto scikit-learn that like did meta learning around a machine learning pipeline that does Bayesian optimization, builds an ensemble in the end. It's pretty complicated. People didn't like that so much because they had trouble implementing it themselves and porting it to GPUs and whatnot. And you don't need any of this. It's just a forward path. And you could like put this into a sensor, and then on a sensor with Onyx, you have not just the model running, but you have a machine learning algorithm running that's actually learning on your data. It's kind of cool. You could integrate it into Excel or whatnot just much more easily than just an AutoML pipeline. Quantitatively, these are numbers from the 2023 paper. It did better in 1 second than any other machine learning or AutoML method in 1 hour. Disclaimer, these are average results, not in every single data set. That doesn't work so well. And it has lots of limitations, but the speed ups were like Auto-Learn was actually the best back then, still a bit better than Auto-Learn. Auto-Learn improved in the meantime. But yeah, this is an hour, this is a log scale at 0.1 seconds. So on a GPU, it's 36,000 times faster. If you only have a CPU, you're only 3,600 times faster. But it's when I saw this blew my mind. I was like, okay, we need to really push on this. It was severely limited, so we only had like 1,000 data points, 100 features, 10 classes, no categorical features, missing values, uninformative features, only classification, not regression, and we had a high inference time. Why high inference time? Because you push everything, the entire data set, into the context in order to predict for a new test point. So actually, there is no distinction between training and inference. It's just always through a forward path. So then there was like expensive. In the meantime, we resolved a lot of this. Up to 10,000 data points, 500 features. Now also do categorical features, missing values, uninformative. Now also do regression and do some KB caching for moderate inference time. Now for these constraints, in 5 seconds, we're better than any other method in 4 hours. So yes, a lot as before. What have we done in order to get there? So we scaled up everything, just a more efficient attention, some changes in the architecture that I'll talk about, inference speed up, so that the KB caching. We improved the prior in many different ways. So in particular, we put trees in there in order to really tell it that there is discrete variables that has these very discrete structures. We support different activation functions like sinusoidals, and in order to tell it that there might be these cyclical patterns. This has categoricals in the prior already, rather than afterwards, and just a lot of engineering to get things right. And we also demonstrated some foundation model capabilities. The new architecture now is actually this axial architecture. So we have axial attention. So we have one attention over the features of the row, and then one attention across the data points with the same feature, and we iterate over that. And then of course MLP. And yeah, then in the end, just predict for like after the 12 layers, we just have another simple algorithm to get the predicted distribution. Before that, we didn't have this axial attention, but we just had one embedding for the entire row, and that makes things complicated. If you wanted to have like not 10 features, but like 12 features, we would have like, or like 8 features, we would have the 0 pad and so on. We don't need to do any of that anymore. This excellent attention allows us to just actually generalize in both the features and the rows. Yeah, qualitatively, TabPFN can fit a very broad class of functions now. So up here we always have the true function, and then here TabPFN and the different algorithms, for example, CatBoost. So for a function like this that is clearly a sinusoidal, then TabPFN would interpolate, whereas CatBoost would just repeat basically the individual points, like x squared. CatBoost would just be these very discrete constant predictions, whereas the TabPFN would interpolate. Of course, linear functions can't do anything with quadratics. Step functions is something that MLPs or neural networks are just really typically very bad at. So here's the MLP can't deal with this so well. But yeah, TabPFN has actually learned through this prior that there is such a thing as step functions and very discrete functions. And yeah, it can model noise. CatBoost would just interpolate constants. Also with predictive uncertainty. Predictive uncertainty can also be heteroscedastic. If you tell it that in the prior, we did tell it that in the prior that there's that it is possible that there's different noises at different levels, then it can also predict that when it sees data like this, where there's just a lot more noise on one side than on the other side. All right. The multimodal predictions are nice. So here's an experiment from this double slit experiment where we have the truth, so this interference pattern of light with a wave particle duality of light. So we have the true function like this, so little sinusoidals, and TabPFN matches that quite nicely, whereas CatBoost that doesn't as well. So and this is so for each point, this is like 5 modes here. Right. So and this basically the x is the input, and then for this x it wants to predict this distribution versus. All right. Then quantitatively, what did we do? We looked at the OpenML benchmark, which is the best available curated data set collection. Looked at all the data sets with less than 10,000 points and 500 features, and for cross-validation, averages, and used a single train TabPFN throughout everything. And it's actually not very expensive to train. So this was trained for 5 days on one machine with 8 2080 GPUs that are really bad old consumer cards. So this costs maybe like $1,000 or $2,000. It's not your billions of training.
You're training based on synthetic data prior.
And that is one run of training. Over these 130 million synthetic data sets.
And what do we do with the 29 data sets?
So on the 29 data sets, we do a forward pass.
That's your just test set.
Yeah, well,
It's not using.
it's a meta test, so it's meta learning. There's basically 130 million meta trained data sets that we do a lot of computation over during algorithm development. Then we have developed the algorithm, and we give it the train split of the meta test data set and predict the test split of the meta test data set. Yes.
On each of the 29 data sets.
I have not. It's sort of like 20. 10. Sam always has 20. We should really. Hey, that's my student. He's on the page.
10 to 20.
I trust him more. I trust him. But we also have an ensemble of 5 different models in there. All right. So yeah, results. How does this work? I talked a lot about gradient boosting. There's other algorithms. There's like linear methods. There's MLPs, SVMs, random forest, light GBM, CatBoost, XGBoost, and they get better and better. And then TabPFN is a bit better, and you zoom in, and sort of all the gradient boosting algorithms are sort of here. better than a random forest, but TabPFN is yet better. And the dark blue versus the light blue, the dark blue is actually just a forward pass. And so just a forward pass here in 4 seconds is better than tuning these with hyperparameter optimization. And then you can also do some hyperparameter optimization on top here and get a little bit better. But you just really don't need it. Yeah, and so here's the same in terms of over time. This is the aggregate results, of course, over data sets. And here is this plot I showed in the title slide. This is one of the data points, one of the data sets, and these are the 28 other data sets that rate better. And then after tuning, well, there are 3 data points, data sets here where cut boost is better. So sometimes tuning cut boost is also better. For TabPFN, you can actually tune different preprocessings, and we have like 5 different, slightly different architectures. Where like sometimes we actually swept some things under the rug, but sometimes we actually do an embedding not just for 1 cell of this matrix, but for 2 cells, and that actually sometimes is better. So little choices like that we can tune over.
So supposedly the tuning will be over the synthetic retraining data.
No, this is what you do on like for cut boost, for example, you know what you do there, right? Different
Just for yours, I don't understand yours. So you've already pre-trained it on these 30 million synthetic data sets, like everything is the transformer is already trained.
Yeah.
What's
And
it?
we train 5 transformers, not just 1.
Okay.
Right? And then it's different preprocessing. So for example, we can like rotate the features or not rotate the features.
But I come to you with my data set.
Yes.
Well, how would you use my data set to fine tune your model?
It's not fine tuned.
Tune it, okay.
We're not changing the weights of the transformer.
But you're tuning something.
We're tuning the hyperparameters. Sure.
Think of prompt tuning. So this is like prompt tuning. Yeah. Or temperature scaling.
You could see it as prompt tuning, but like choosing the right architecture.
Yeah,
but for example, we could, and we don't tune the entire prompt, but we tune like let's use this different scaling mechanism, for example, like let's do a plot scaling before we put it in or something like that. That's one of the choices. Let's do a standard normalization. Let's do like e to the power of your data and throw this in and see what's better.
Okay, this is that happens before you generate the string text, the text that I
Yes,
should
so it is prompt tuning in the sense that you, in a non-gradient based manner, generate different inputs to the TabPFN from your data. Yeah, very good. Right.
I think it would be 1,000 words here. I feel like you're missing a figure to show us all this process.
That's true. Okay, regression, the results are not quite as good for regression. It's also better, but yeah, for clarity, it's not quite as good as for classification. And then we also looked against the best methods for AutoML. But that is currently AutoGluon. And so here we have the blue is the TabPFN as before, and in classification, even the 5-second run is better than AutoGluon after 4 hours. But you can actually make it yet better by a post-hoc assembling, which is the main method that AutoGluon is based on. So we assemble different predictions of different types of TabPFN, of different hyperparameter configurations, and assemble that in a clever way. And that clever way is the one thing that AutoGluon put on top of Tabular in order to make AutoGluon yet better. And a lot of great engineering. Yeah, and for regression, you really need this in order to beat AutoGluon. Like there, the standard just a forward pass is actually worse than AutoGluon by a fair bit. And do some hyperparameter optimization to tie it roughly, and with also for solving it.
TabPFN's performance changed with time. Doesn't it just make a forward pass?
Yeah, so this here is a forward pass, but cut boost is also just like with hyperparameters, it actually also just makes a prediction, but this is over time when you tune hyperparameters. So like if you just take the default and run it, it exists. But then if I give you an hour, you're like, well, I made my forward pass, I'm not going to use that hour. That would not be as good as, well, if I have an hour, let's try this other hyperparameter. Let's try this the cross-validation, internal, inner cross-validation in order to pick the one that's better on the cross-validation.
Are those 4 hours used, like are you using something that's up to over hyperparameters? Like some of those gradient boosting methods have like 40 hyperparameters.
Yeah, so we did, that is one way in which many of the deep learning papers just really failed properly tuned boost, not training with the right hyperparameters. It's sort of just always done based on random search because nobody likes based on optimization, nobody likes it a lot. So yeah, it's based on random search. Also, our optimization of TabPFN is based on random search here. But yeah, we put a lot of emphasis into choosing the right ranges and the right hyperparameters to tune because yeah, if you tune the wrong hyperparameters, you can arbitrarily that. We follow a lot of the results in the literature or the good configurations in the literature. Although we want to put a lot of work into choosing the right ranges because it then depends on these. And yeah, so we piggyback on that a lot and also tried like 4 different types of hyperparameter spaces from different papers. So and I'll always pick the best one. Then it is very meticulous about this. Yeah, because that is really, yeah, then there was a lot of the downfall of the previous deep learning methods. All right, conscious of time, okay. So just some ablation results. So it is now robust against uninformative features. Here and this is simply by telling it in the prior that, well, sometimes there's uninformative features and just learn not to deal with these, learn to just ignore these rather than seeking signal in every feature. So here we added like 9 times the features as uninformative on top of it, and it can now deal with it, whereas TabPFN V1 had like was really bad. There and MLPs, for example, like the performance just really plummets when you add these uninformative features. But you can put this in the prior and that's fine. Same with missing values. Just much worse. Same for categorical features. So this here is just data sets with and without categorical features. It's not that we made them categorical, that it's actually worse now for categorical.
So missing values is within a feature, or are we talking about missing features in the structure?
It's missing values, so not missing. Missing features would just be latent, so it would be okay.
So the latent was already
like entire latent, but this is more missing value. So you have a feature that is active for some of your data points, but not active for others. With I think up to quite a lot, but I sometimes, but mostly not that much. But yeah. And well, we didn't make the test data set, so I actually don't know what this is. But and we also had some. We did some research looking at missing at random versus missing not at random and so on. In the end, we actually only used the missing at random prior because it didn't really matter. But we had some results if you really know it's not missing at random. Like if you have a questionnaire and the question is, well, do you smoke and what's your age? And if the age is 12, then they're smoking, then they're not going to put yes. So that's missing not at random. That's you can't put that into the prior, and it's going to be better for those particular cases. But we didn't see that in a lot of real data to make it worse putting that in the prior.
But that's what I don't understand. What does mean putting in the prior? So you're doing this pre-training once, and you're changing the prior.
And of course, in developing the method, we played with a lot of different things.
Okay. But nobody's going to go and change the prior now, right? It's going to be a foundation model.
We are still doing.
Okay.
All right.
It's great to see the level of interaction. I've been part of the problem. Frank is almost out of time. Let's have a moratorium on questions until he gets to his conclusions.
That's cool. You gave me the 5 a minute or 2 ago, and I shall make it
That's good.
Yeah, so it also works well with less samples. So in particular, with half of the samples, it's as good as the next best method with all the samples. So if you are in situations where, I don't know, you're running medical studies and you have the choice of onboarding 5,000 people or 10,000 people, you'd much rather onboard 5,000 people if you can get to the same predictive accuracy. There's a demo, so you can download it if you want. This will be there in the final slide again, so don't worry if you didn't make it now. This is a penultimate slide. We also have foundation model capabilities. So for example, we can do fine tuning. So we pre-trained on the synthetic data, but we actually, if we fine tune on some real data, it gets better on that real data. If we fine tune on some real data from a particular domain, it gets better on real data from that particular domain. Just like if you download your llama and you fine tune it on your data, it's going to do better on your data. The plot here is this here is the original not fine-tuned TabPFN. The orange is the true prediction, and then it just doesn't know that this is a sinusoidal pattern. So blue are the predictions of TabPFN. And after you have fine-tuned it a little bit, like very little bit, on a couple of functions of sinusoidals, it kind of figures out, oh, this is probably a sinusoid. We can do prompt tuning. We had a Neurospace paper on that. We can use it for synthetic data generation. We had a Neurospace paper on drift resilient TabPFN, which, when you have drift in your data, it can take that into account and you can tell it what you don't need to tell it that there's drift. But if you use a different version on the non-drift data, it gets slightly worse, but if there's drift data, it's much better than the original data. We have a version on counterfactual fairness, so that's maybe to the point where we're kind of looking in causality, but there's also questions there how our current model might this is actually different than how this is interventional. One can do a hypernetwork to output a fast predictor in the end in order to so not output just the prediction, but output the weights of the neural network that is at a child network that is different. And you can also output a GAM instead, a generalized additive model, which is super interpretable. And so it can also be seen as a different way of training a GAM. With that, takeaways are TabPFN is hopefully on its way to become a new default for tabular machine learning. Currently, it will be the default for up to 10,000 data points, 5 features. You can already try it out. Love feedback, so if it doesn't work for you, please let us know. Because we want the reception of this to be good when it comes up. It's a different paradigm for data science and what we have so far. So far, we are very much like, which is the right model for this data, which are the right hyperparameters, and that's very model-centric. And I'd love to get to a more data-centric part where the data scientist says, I expect these types of patterns. I expect that A causes B. Just factor that into your model. So that's some of the stuff we want to do, make it promptable, make it interactive, make it promptable through language, interact with the data scientist, with the non-technical people to tell us about the data, and just directly take that into our model and make better predictions. And just really allow quick iterations with the user rather than this old-fashioned AutoML approach that runs over everything. All right, with that, thank you very much.
Well, friends, you had enough questions that any reasonable person could want during this talk. And then one or two more before we call it a day. And maybe let's favor people who haven't asked questions during the talk yet.
Thanks for a great talk. I have a general question. Like when we talk about like visual foundation model or language foundation model, because they share like the very high like same philosophy like large language model. Why we expect foundation model for large language model? Because we want the model to speak like humans, and for the visual foundation model we want, because when we look at things and we know there are some visual maybe inside the relationship is smooth, something like that. So I'm not quite sure why we can expect a good foundation model for all tabular data. It's like for tabular data, we can have many independent tasks. If this group task and they are totally independent with another tabular data. So why should we do like building a foundation model for all this? I can understand like you train a lot of things and based on in-context learning, and we can do it very good and beautiful with a unified model and apply to all our tasks. And I'm not quite sure like what kind of real thing, like if we put all the data together and train model, and what's the real thing? The real thing is model. Like for visual, maybe they learn something like visual parts. We understand the parts of the
Yes,
image.
so I think here is very much that's why I kind of keep on emphasizing the causality. I think we do learn patterns, like, oh, this looks like here, this looks like A causes B just from the data. And then, well, we build the Bayesian posterior over structural causal models where A causes B, that is more likely than one where B causes A. And so we look more at predictions of the structural causal models where B causes A than where A causes B. So it sort of figures out the patterns that occur in structural in data sets, and so it's also sort of it's this pattern of sort of AutoML where they are of machine learning in general, where like throughout the history of AI, it just happens all the time that manually derived components are replaced by automatically found components like sift and park features or endgame libraries in Go and whatnot. All of this is replaced by learned algorithms, and we now have a learned algorithm that replaces a handmade XG boost. I mean, that was also handmade. And it has, they make certain assumptions about the data, and this makes different assumptions about the data. And the nice thing is here, you can hack it. You can say, I want these types of assumptions of my data, and then it gives you posteriors about these types of assumptions. And in the future, we want to get to a point where, yes, we just have this one foundation model, and you can actually prompt it with your prior, and then you don't actually need to make a new TabPFN.
So it means that model can also learn causal structure. And that's point to, when we have the context, and this model can just point to this data as causal structure and do the prediction.
Yeah.
Right, so let's have maybe a question for somebody else at the end of our time. Is there anyone else who wants to take us home? Yeah.
So how does it scale with dimension of the features? Like I'm slightly worried. Are you still doing like a causal mask? It feels like this would be.
Yeah, so we're not doing a causal mask.
Fully quadratic.
Yeah, so we're quadratic in the number of data points plus quadratic in the number of features. Previously, we were just quadratic in the number of data points, but the embedding was much larger. So now the embedding is much smaller, but quadratic plus quadratic. Of course, there's linear attention. We have a version of Mamba retesting is not working that great, but linear attention is working better. Actually the training was only up to 2,000 data points, not even to 10,000. So we could, just for cost reasons, but all the testing is up to 10,000. So it just generalized from 2,000 to 10,000. But obviously we can make it better, and so we want to look at scaling laws.
All right, let's leave it there. Thanks for really.